Welcome to today's session in physics. Today we start with the new chapter, that is chapter 6, Electromagnetic Induction. We have already discussed the relation between electricity and magnetism. In the previous chapter we discussed current produces magnetism or magnetic field. Around a current carrying conductor we have evidences of magnetic field. So in the end of 19th century, this was a question in front of the scientists, that whether the reverse is possible. That means whether magnetism can produce electricity. Finally, the answer came from Michael Faraday, a famous scientist. So in this chapter, in the introduction, we'll be discussing Faraday's and Henry's experiments which led to the formulation of the law of electromagnetic induction. In his experiment, Faraday took a bar magnet and moved it towards a coil which is connected to the galvanometer. In the galvanometer, he could see a deflection. While moving towards the coil to one side and while moving away from the coil, galvanometer showed deflection in the opposite direction, which is a strong evidence of presence of current in the coil. Actually, this is the principle behind the generator, electric generator, whether it is AC or DC generator. This is the principle behind, and we are going to discuss about this principle. Now coming to the experiments in detail. So when the bar magnet is moved towards the coil, the galvanometer showed deflection towards right, and when it is moved away from the coil, it shows deflection towards left. Note that it is the north pole which is moving towards and away from the coil. When the bar magnet is at rest with respect to the coil, it is found that there is no deflection in the galvanometer. Now he repeated the experiment with the south pole moving towards away and towards the coil. So he could see that when the south pole of the bar magnet is moved towards the coil, the deflection is to the left side, and when it is moved away from the coil, the deflection is to right side. It is a point to be noted that the galvanometer shows deflection only when there is a relative motion between the bar magnet and the coil. If the bar magnet is in the state of rest with respect to the coil, there is no deflection in the galvanometer. From this, Faraday concluded that it is the relative motion between the coil and the bar magnet which induces a current in the coil, and he called that current as induced current. In the second experimental setup, Faraday took two sets of coil. One coil is connected to the galvanometer, that is C1, and the other coil C2 is connected to the battery. So current is flowing through C2. And the steady current flowing through the coil C2 produces a magnetic field around it, and the coil C1 is linked with the magnetic field produced by the coil C2. In his experiment, Faraday moved coil C1 towards the coil C2. That means C2 was kept stationary and C1 was moved towards C2. When it is moved, he could see that the galvanometer showed a deflection towards left side. And when it is stationary, there is no deflection. And again, when coil C1 is moved away from the coil C2, the galvanometer shows a deflection towards right. In the next stage of the experiment, Faraday kept C1 stationary and moved C2 towards C1. So when the coil C2 was moved towards C1, he could see a deflection towards left. And when it is stationary, again there was no deflection in the galvanometer. When the coil C2 was moved away from the coil C1, the galvanometer showed a deflection towards right side. From this experiment, Faraday concluded that it is the relative motion between the coil C1 and C2 which produces an induced current in coil C1. In the third experiment, Faraday took the two coils C1 and C2, and C2 was connected to the battery through a tap key. So when the tap key is pressed, the current flows through coil C2, and when the tap key is released, the current stops through C2. That is the arrangement of tap key. In this experiment, there was no relative motion between C1 and C2. And what he could observe is the moment when the tap key is pressed or released, the galvanometer shows deflection. When the tap key is kept in pressed position, there was no deflection found in the galvanometer, only when it is pressed or released. And also when an iron bar is inserted coaxially inside the coils, the deflection produced in the galvanometer was found to be more. From this, he concluded that since there is no relative motion between the coils, it is the changing magnetic flux linked with the coil C1 induces a current in the coil C1. Since there is a change in the magnetic flux linked with the C1, that changing magnetic flux only induces a current in coil C1. This was concluded by Faraday. We know that mathematically the magnetic flux is given by phi b equal to b dot a, that is b a cos theta, where b is the magnetic field, a is the area, and theta is the angle between the two vectors b and a. And magnetic flux is a physical quantity which is proportional to the number of field lines passing normally through an area. Faraday analyzed the observations of the three experiments once again. He called the potential difference which is induced between the ends of the coil C1 as induced EMF, and it is the production of this induced EMF which makes a current flow through the coil C1. And he concluded that in the first experiment, when the coil is kept stationary and the bar magnet is moved, the magnetic flux linked with the coil is changing. And it is that changing magnetic flux linked with the coil produces or induces an EMF in the coil called as induced EMF. In second experiment, current flowing through coil C2 produces a magnetic flux or magnetic field. So when there is a relative motion between coil C1 and C2, there is a change in magnetic flux linked with coil C1. And this changing magnetic flux only induces an EMF in that coil C1, which in turn produces current. In the third experiment, when the tap key is pressed or released, that moment there is either a rise in the magnetic flux or a decrease in the magnetic flux linked with the coil C1. This increase or decrease in the magnetic flux linked with the coil C1 induces an EMF in that coil. This is the reason why the coil C1 or the galvanometer connected to the coil C1 shows a momentary deflection when the tap key is pressed or released. So it is a point to be noted that when there is no relative motion, as we said in the previous experiments, there is no change in magnetic flux linked with coil C1 and there is no induced current. Here also, when the tab key is kept in pressed state, there is no change in magnetic flux linked with coil C1. Even if there is a magnetic flux, there is no change in magnetic flux linked with C1. That is why there is no current. From these experiments, Faraday concluded that it is the time rate of change of magnetic flux which induces an EMF in the coil, which in turn induces a current which is called as induced current. From these observations, Faraday reached at his law of electromagnetic induction. According to the law of electromagnetic induction, the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. Mathematically, the law can be stated as induced EMF E is equal to minus d by dt of phi b. Here E represents induced EMF and phi b represents the magnetic flux. The letter epsilon also can be used to represent induced EMF. Here the negative sign stands for the direction of induced EMF and hence the direction of current, which we will be discussing in detail with Lenz's law in the next session. Now we can see that we can increase the deflection produced in the galvanometer by increasing the number of turns in the coil. By increasing the number of turns, the induced EMF produced is increasing. So we can modify the mathematical statement as E is equal to minus n d phi by dt. Here negative sign shows the direction of induced EMF and hence the induced current. So once again, Faraday's law of electromagnetic induction states that the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. And the final expression we have, the induced EMF E is equal to minus n d phi b by dt. With that, we conclude today's session. Thank you.